Welcome to this last segment on logical equivalence. In propositional logic, we say that two propositions are equivalent if they are always true at the same time and always false at the same time. Well, this concept carries over to predicate logic. However, the definition of logical equivalence in this system of logic is a little bit more complicated because now propositions can contain variables as well as predicates. So here is the definition for logical equivalence, denoted with the same symbol as in propositional logic. In predicate logic, we say that S and T are logically equivalent if and only if they have the same truth value at all times, and in particular, they have the same truth value for all possible domains of the variables that these propositions contain. And also, they have the same truth value no matter which properties or relationships the predicates in these propositions represent. So notice the definition is a little bit stronger than in propositional logic. In other words, you have more things to check to prove that two propositions are logically equivalent in predicate logic. So here is our first example of a logical equivalence between two propositions in predicate logic. Now, to demonstrate this equivalence, we must argue for every possible domain of the variable x, as well as for every possible interpretation of the predicates p and q. And to do this, I'm going to describe an argument that doesn't make reference at all, or doesn't make any assumption about the domain of the predicates. Therefore, whatever argument I am making will be general and will hold regardless of which specific domain or predicates I'm using. And the argument is going to go like this. It's going to be an intuitive, not a formal argument. We're going to argue that whenever this is true, then this proposition must also be true, and vice versa. Whenever this is false, then this proposition must also be false. In other words, these two propositions are always true in the same cases. So the first part is to assume that this proposition is true, which means for all x in a domain, whatever the domain, this proposition is true, meaning at the same time p of x must be true and q of x must be true. And this is true for every x in the domain. So obviously in that case, it must be true that p is true for every x in the domain and also q is true for every x in the domain. Therefore, this proposition must also be true. Now in the second part, let's assume that this proposition is false, which means there must exist at least one x for which this conjunction is false. And a conjunction is false when either p of x is false or q of x is false. So that means there must exist at least one x in a domain for which either p of x is false or for which q of x is false, or both. But one is enough to guarantee that this conjunction is also going to be false. And that is the intuitive proof of this first logical equivalence. For this second example of a logical equivalence in predicate logic, the proof is similar, and I'm just going to state it much faster. Again, we're going to argue that for any domain and for any interpretation of the predicates p and q, the truth value for this proposition must always be the same as the truth value for this one. And the reason for that is if this is true, that means there must exist at least one x for which this disjunction is true. And a disjunction is true if either the first operand is true or the second operand is true. In other words, there must exist an x for which p of x is true or for which q of x is true. So intuitively, those two propositions are indeed equivalent. Notice how the only difference between those two equivalencies are the different quantifiers and the replacement of conjunction by disjunction. Now let's look at a third example of a logical equivalence. Actually, this one we already saw in a previous segment. It says that the negation of a universally quantified proposition is an existentially quantified negated proposition. Now, we already proved this equivalence earlier. Remember that for all x, p of x is equivalent to a conjunction, and there exists x something is equivalent to a disjunction. And remember how we proved that the negation of a conjunction is a disjunction of the negations. In fact, that's an example of De Morgan's law, so we can call this logical equivalence another De Morgan's law, but this one is for all quantifier. And of course, if there's a De Morgan's law for all quantifier, there's also a De Morgan's law for there exists quantifier, namely the negation of an existentially quantified proposition is a universally quantified proposition of a negation. Again, the negation of a disjunction is logically equivalent to the conjunction of the negations. So we'll call this fourth logical equivalence the De Morgan's law for the existential quantifier. So these last two are extremely important since we'll be using them all the time. So the way to remember them is that if you start with the negation of a quantified proposition, you can move the negation across or in front of, well, actually across or after the quantifier. So notice how the negation ends up here. However, in the process, you must flip the quantifier from one type to another. So if it was a for all quantifier, you have to flip it to an there exists quantifier. And if you started with a there exists quantifier, when you move the negation across the quantifier as we did here, then the there exists quantifier becomes a for all quantifier. Now let's consider a fifth example of a logical equivalence. And this one we're actually going to prove formally, so you have one example of that process. So how do we prove that two propositions are logically equivalent? We can proceed as we did with propositional logic, namely using equational reasoning. Remember, in that process we start with one of the propositions, let's say the one on the left, and we successively rewrite it using known equivalences until we end up with the second proposition in our equivalence. So starting from the first one, what can we do? Well, we have the negation of a universally quantified proposition, so we can use the De Morgan's law for the universal quantifier as we just explained it. And here is what we get. Notice how the for all quantifier switched to a there exists, and the negation now appears after the quantifier. Now, we have a conditional, so we can always replace the conditional with a disjunction, as we saw in the previous lecture. P of x implies Q of x is equivalent to not P of x or Q of x. Remember, we didn't give a name to that logical equivalence other than calling it with the asterisk. Now, we're not there yet, but we're pretty close. So the next step, I hope you can see, is to apply the negation to the disjunction. And to do that, we use the De Morgan's law, and resulting with this equivalence. Notice how the negation of not P is not P, and the negation of Q is not Q, and we switch the disjunction to a conjunction according to De Morgan's law, the second one. And finally, we can get rid of the double negation using the double negation equivalence. And lo and behold, we end up with the second proposition in our logical equivalence. So this is an actual proof, a formal proof of that equivalence. I just wanted to give you at least one example so you know how to do those. Now, intuitively, why is it the case that this equivalence holds? We should always check our intuition here. Well, this says it's not the case that for all x, p of x implies q of x, which means there must be at least one situation where the conditional is false. And the conditional is false when p of x is true and q of x is false. Therefore, if this proposition is true, there must exist at least one x for which p of x is true and q of x is false. And that is the meaning of this logical equivalence. Before we move on to the next example, remember two things. First, do not forget to justify every step in your equational reasoning. Every inference must be justified by a named or well-known logical equivalence. Second, notice how we used equational reasoning to prove this equivalence. So why didn't we use a truth table? Well, it turns out it's not possible to use truth tables anymore in predicate logic. Think about it. How many cases would you have to consider? Well, in this case, unlike in propositional logic, we're not going to consider propositions P or Q, which can only be true or false. We're considering predicates, say P of X, which is actually a property of a whole set of objects, which itself is defined by a domain. So there's no way to build a truth table here for any of these propositions because we haven't even specified the domain nor the meaning of the predicates. So just remember that in predicate logic, we can't use truth table algorithms anymore to prove interesting results. That's why we used equational reasoning in this case. Now, let's turn our attention to the next logical equivalence. Now this one I'm going to let you work on your own, so please pause the video and prove whatever needs to be proved here. So it turns out that this is not at all a valid logical equivalence. In other words, those two propositions are not logically equivalent. The way you prove that is most likely by coming up with a counterexample. And remember those drawings that we made earlier, they would come in pretty handy here to come up with a counterexample. And I'll let you do that on your own if you haven't done so yet. So remember here, before you start proving anything, I hope you use your intuition to try and understand what those two propositions actually meant, and then hopefully quickly realize they were not equivalent, and then were able to prove that. Let me conclude this segment by giving you a piece of advice on how to translate from English to predicate logic. Let's say you're given a problem in one of your computer science classes and you infer that, yes, there exists a recursive algorithm to solve this problem. How would you translate this sentence into predicate logic? Well, clearly you would use an existentially quantified conjunction like there exists X such that X is an algorithm and X is recursive. Be aware that other ways of phrasing this fact in English would also be translated with this predicate logic proposition. For example, if you said some algorithms are recursive, you would also end up with such a proposition. As we argued before, remember, this as the form some A's are R's and gets translated like this. So I'll let you think about the meaning of these two sentences and make sure you realize they are identical. The problem I want to point out is the fact that many students actually translate one or two of these sentences using a conditional instead of a conjunction. Now we just argued on the previous slide, that was example number 6, that these two propositions are not logically equivalent. In fact, this one is wrong. It's wrong because you're using an existential quantifier with a conjunction, which is not a good idea. Just remember that. It's okay to use a universal quantifier with a conditional. In fact, we've done so before. This is the kind of sentence of the form all A's are R's. In this case, all algorithms are recursive. So here is the rule of thumb I want to emphasize here. it's okay to use the universal quantifier with a conditional, and it's okay to use the existential quantifier with a conjunction. But it's usually a bad idea to use the existential quantifier with a conditional. In fact, you should probably never do it.